Okay, so the first thing I wanted to say is that I'm not the quantum expert, like Matt just said, and so you guys will have to stick around for tomorrow morning when Jerry Chow from IBM is actually going to present the IBM quantum computer and is going to tell you a lot about the research that we're doing and the quantum computers we've actually already built in this field. So as Matt said, I'm more of an optimization expert, so I'm here to give you the current status of optimization applications and opportunities in these two fields, transportation and manufacturing. So typically when I walk into customers, they ask me, okay, well, how hard is this problem that we just explained that we're having? How hard is it in relation to other problems that you typically see out there? And I've learned very quickly that actually you have to say your problem is actually quite complicated. If you say that it's very simple, then they actually take that personally, and it's like calling their baby ugly or something, right? So you have to be careful there. But in general, the rule of thumb is that the closer you are to actual operations, the harder the problem becomes, right? And so when you work on strategic problems, problems that are looking maybe a 5-year horizon out, and you're maybe calculating capital expenses, where to place a warehouse and how many planes you're going to need or how many trucks you're going to need or big investments, then the problem is much simpler, and that's when you do the strategic planning, right? But when you do operational scheduling, then things become much harder. And there are a number of reasons why. First of all, integration, right? So with operational scheduling, you need very tight integration. With strategic planning, you can even get away with manual I/O. Requirements. Actually, with strategic planning, you can get away with making a lot of assumptions. With operational scheduling, it's actually you need to define lots of different exceptions and how the optimization solution and the model needs to respond to all these exceptions. The interaction, right? So for strategic planning, you have typically experts that are doing, designing different scenarios. They need to run different what-if solutions. But in the realm of operational scheduling, you actually, most of the time, you're working with an existing schedule and the expert or the operations person is tweaking that schedule, and then you need to repair it. So ultimately, the optimization solution is actually just repairing a schedule, right? And that's a key thing we're actually going to see in much more detail in the following slides. And then obviously, you don't care about optimality when you're doing operational scheduling. You just need a good enough solution. And your users are different, right? So on the one hand, you have business experts with many years of expertise. On the other hand, you might have just operations guys, obviously. And then finally, the performance requirement is very, very different, significantly different, right? So the business expert might be willing to set up these what-if scenarios and kind of go home and come back the next day and see what the results are. But the operations guy is dealing with kind of a fire drill, and he needs results basically right this second, right? And he needs to make a split-second decision. And because of these last three areas here, we believe that that's really an opportunity for quantum to step in, especially with the performance improvements that we hear and we've heard from other speakers that are coming in the near term. We can potentially kind of fix all these areas in kind of these last three dimensions here. And obviously, IBM and other vendors have been very successful in solving the strategic planning problems, and we've been somewhat successful in solving some of the operational scheduling problems. And I'm going to highlight some of them that we're sort of had some success in, but some others are actually very, very hard and very complex. And we really are in desperate need of quantum to step in and actually deliver these performance improvements to actually solve these very practical applications that occur on a daily basis. So I'm going to start with airline operations as opposed to transportation as a whole. Airlines are actually very mature users when it comes to optimization applications. They've been using them since the 80s. They have pretty big operations research departments. And since the 80s, they've had solutions like, for example, yield management and price management, right? And that's the reason why when you check the price for a ticket, let's say from San Francisco to New York, and you check it today, and then you check it tomorrow, you're going to get potentially two different prices for the same airline, right? So that's optimization for you in practice. But the really big problem with airlines, and even though they have all this expertise and they've actually kind of decomposed the problems in terms of like a business decomposition, so they're solving problems, maybe a month ahead of time or a few months ahead of time, and they're looking at several issues ahead of time and actually building a plan ahead of time. The problem is at the point of impact and when the kind of planes are in the air and you need to make split-second decisions and you have this thing called irregular operations, right? And that kind of throws a wrench into pretty much everything, right? And so there are some controllable causes as to why irregular operations occur and why delays happen, right? So you might have some last-minute plane changes, or you might have some last-minute maintenance actions that you need to take on a plane, or a ground crew is taking longer to do the refueling, or carry the baggages, or whatever, right? And that causes some issues, and they're controllable because if you had scheduled your ground crews better, or if you had done the maintenance last night, then you wouldn't run into those problems, right? And then the uncontrollable causes are things like weather and air traffic control and security and medical, right? And there's a huge opportunity in this space, right? So the International Airline and Transportation Association, I believe, they're estimating basically 15 to 22 billion USD per year in terms of recovering from these issues more efficiently, right? And you might think this number is pretty big, and you might be saying, well, you get a 30-minute delay, and how come this kind of 30-minute delay for a flight somewhere kind of can balloon to this number? But then you have to think that the schedules are actually very, very tight, right? So those delays typically cascade over time across the entire network, right? So if you have a single flight, here in San Francisco basically getting delayed, then the flight after that, the flight segment after that is also going to be delayed for that same aircraft, and also the crew that is manning this flight today is also going to be delayed in their next flight. So it has a very quick cascading effect down the schedule, and it really balloons out of proportion very, very quickly. So here's a map, basically, of the different optimization problems across the strategic and tactical and operational dimension, and also across this other dimension where I have crew and ground issues, equipment issues, and maintenance issues. And these applications, I'm not going to go through all of them in a lot of detail, but I'm just going to say that we have a pretty good handle in solving these problems, right? So obviously, performance, yes, could be better, but we're currently doing a pretty good job in solving this. And as I said, there are big teams inside of airlines that are solving these problems, and they're doing it with in-house solutions, and there are some software vendors that are solving these problems, and there's obviously IBM tools that you can use to solve these problems as well. We're doing a slightly, maybe not as good of a job solving these problems, which are closer to the kind of operational or real-time time frame. These are probably calculated maybe a week out, maybe a few weeks out, right? So things like scheduling ground operations and tail allocation and light maintenance. And finally, we get here, and I think this is where the real opportunity lies, right? So figuring out how to do pretty much real-time response to the schedule breaking, and then figuring out basically how to repair that schedule. And there are some cases there, actually, rebooking is the one example on this map that it's actually pretty well contained. And actually, if you've flown recently and your flight got canceled, you were that lucky, then you might have seen that you got rebooked actually pretty quickly, right? And the reason for that happening is that actually rebooking is kind of self-contained, right? So it just affects the passengers, but it doesn't have this cascading effect, right? Obviously, it kind of ruins your day that your flight is getting canceled, but it doesn't really affect anything else in the operational network from the airline's perspective and from kind of the crew's perspective. So So actually, most of the airlines have automated rebooking solutions, but they're actually lacking in some of these other solutions here. So I'm going to talk about this one in particular, and this one has to do with maintenance events. And whether you believe it or not, actually, the airlines maintain a list, basically, of their equipment, as you would expect. And right next to each aircraft, there is a huge other list of all the checks that need to be performed that are getting close to critical, right? And these might be FAA regulated, or there might be other checks basically that they have to perform maybe in the next 2, 3, 4, or 5 days. And based on the landing cycles, how many landings and takeoffs that the aircraft perform and how many miles they fly, these timers basically trickle down, right? So you might have planes that are critical in the next day, or you might have planes that are critical in the next couple of days, basically. And pretty much every night they perform some type of maintenance on some aircraft. And there's a big department, right, that's really responsible for this overnight maintenance. And every day, basically, they figure out that we're going to get so many flights or so many aircraft in a certain repair station. And so we need to figure out, basically, out of the 100 flights that we're going to get, which 20 we're going to work on, right? So that's one problem they solve, and they're relatively efficient in solving that. But then they have to figure out of the rest of the planes, which ones are going to be hitting other repair locations. And if those planes are not going to be getting to those repair locations, then they talk to their buddies over at tail allocation and operations, and they tell them, hey, look, you got to bring plane A in to a repair facility for such and such maintenance check. And so these guys on the tail allocation side, they actually start playing with the schedule. They switch things around, and they call them back and say, hey, look, plane A that you wanted to get to a repair location, we got that covered, don't worry about it. But because they switched everything in the schedule, all these metrics that we had over on the left-hand side, the landing cycles, flight times, have all now updated. So actually, plane A is not the right plane to bring to a repair location anymore, right? And so because of this updated routing, you get to this kind of vicious cycle where you have to kind of repeat this multiple times over and try to get it right. It's a very complex puzzle, basically. And so, and that's a hugely complex problem that we actually don't have very good solutions for. We've tried to solve it, and in some situations, actually, in airlines that have a single hub and a single repair facility, this is pretty simple. But for most U.S. airlines, actually, this has not been solved. So the other thing I want to talk about is divergent management. So obviously operators in airline network control centers are looking at pictures like this, where basically you have the flight paths of several hundred aircraft, and you also have weather superimposed. And one of the key things that happens every so often is that one of these major weather systems goes on top of an airport, right? And as a result, you have a reduction in landing capacity, and the operator needs to figure out one of these three things. Do I divert some planes? Do I delay some incoming flights? Do I put some flights on hold, right? And they actually have to figure it out pretty quickly, right? And they have to do it considering all these things, right? So what is the typical expected reduction in capacity for that weather event? So it could go all the way from full landing capacity to zero if you have a lightning storm, for example, right? Or it could be maybe 50% if you just have heavy rain, right? And you obviously need to look at the scheduled landings at that time. So you need to kind of figure out, okay, how many planes do I divert? And then you have to figure out things like alternative airports and remaining fuel times and all these things. And you really literally have to do this in, within minutes, right? Or you need to start providing some recommendations within minutes of these initial indications that this weather event basically is going to hit the airport. And so this, again, is something that we haven't really solved or we haven't really provided a solution for. And the thing that makes this even more interesting is that obviously weather is very non-deterministic, right? So you might be getting some probability distributions instead of a specific deterministic input in terms of whether that weather event is going to hit the airport and how massive it's going to be, right? So you can potentially think about this problem in terms of a stochastic optimization problem, ideally where you have some prediction that tells you, well, with maybe 20% probability, you're going to get this event that's going to close down the airport. With a 50% probability, it's going to reduce landing capacity by 50% and so on and so forth. And actually try to solve that problem as opposed to trying to solve a very deterministic problem that you're not really sure that that would be the case, that the weather system is actually going to hit for sure that airport. And finally, for travel and transportation, I'm going to talk about gate assignments. And we've talked about these other two problems, and kind of gate assignments doesn't sound as sexy, or as maybe it doesn't have such a big cost potential as some of the other ones that we talked about. But anytime the airplane spends time on the ground just idling and just burning fuel, basically the airlines are just burning money, right? So you're not really helping anyone, right? And you probably, all of you have experienced this situation where you get in maybe 15 minutes early, and the captain is kind of very proud of himself, and he says, well, we got in 15 minutes early. You drive up to the gate, and they get on the AP system, and they tell you, well, we have to wait for 15 minutes because there's another aircraft that's now still occupying our gate, so we have to wait for them to back out, right? And at that time, with those 15 minutes, basically, you're just burning cash. You're not doing anything helpful. So we did calculate at some point when we were working with an airline on this problem that they could be saving maybe close to 100 million a year if we were able to improve this gate assignment, especially for big hubs in the US, right, where you have maybe a single airline taking up 40, 50 gates or something like that. And again, you can imagine the situation is very similar, right? So you're doing some assignments maybe 24 hours ahead based on kind of flight schedule and gate availability and matching of gates and planes. And then during your regular operations, when a certain flight is delayed, you need basically to update this gate assignment, right? And then you got to do it while obviously trying to minimize the idling time on the ground and minimizing the number of gate changes, so you don't want to impact everyone in the airport. And the other thing you want to minimize are the gate changes that you're going to impact for the next hour, right? I mean, that's a critical thing because in the next hour, everybody's already on their way to the plane, right? The crews, the ground crews, the captains, the passengers, right? So you want to obviously minimize that. So that was in terms of kind of transportation in general and airlines in specific. In transportation in general, obviously, you have other problems, but they're very similar to what we discussed, right? So it's always about assets moving to different locations, and you want to make sure that when you're kind of routing the assets to those locations, or the decisions you make on the assets need to be good decisions, because it's not easy to recall an asset once you're moving it to a different location. So we're going to talk briefly about manufacturing. And I have the same map here for manufacturing, right? So we're going to cover some of the applications that are in terms of strategic applications. We're looking at years out, tactical problems, which we're doing a pretty good job at solving most of the time. But the real big issue with manufacturing, and this applies to both discrete and process manufacturing, is detailed scheduling, right? And the big issue with detailed scheduling is that everything pretty much on this graph affects detailed scheduling, right? So it changes based on the number of workers you have available and their skills and certification. It changes based on the inventory targets that you might have gotten from your inventory optimization. It changes based on the balancing between the different manufacturing lines that you've decided to do, on the maintenance events, and also on orders that are coming in from your sales and operations planning system. And finally, also on product changes, right? So anytime time the engineering department or the R&D department comes up with a new product, then that's really going to affect how you're going to actually be able to execute on new orders and on your inventory targets. So this is a typical thing that most schedulers or operations people on the manufacturing floor are looking at. And here we actually have both the issue of just a complete new schedule generation to answer some problems and also schedule repair, right? So before with the airlines examples, we talked mostly about schedule repair, but actually in this case, even schedule generation is actually not a simple thing. Sometimes it could, literally take hours to solve, and it can pose some very interesting business problems, and we would ideally like some solutions for schedule generation. And so here are the key decisions. It's very easy to state, and actually other people yesterday talked about the job shop scheduling problem, and this maps exactly onto that. So start and time, end and time for each task, worker task assignment, workstation task assignment. Very simple to actually state, but there are all these requirements and all these constraints that make these assignments actually very, very hard. And in terms of the objectives, all you need to worry about, manufacturing people are actually tracking several different KPIs like utilization or throughput or WIP inventory or other metrics that actually most of the time end up being irrelevant. What you really care about is whether you're delivering orders on time, right? And whether you're actually building to order or building to stock, and you're doing that on time as promised. So let's go into some of the challenges to see why both of these two problems are actually pretty complicated and pretty challenging. So generating schedules is actually very important for the business because they want to consider some very complicated trade-offs. Things like, for example, what happens if we add an additional shift, right? Will that help us actually make our numbers, right? Will that help us make whatever it is that we're producing in time, right? What if we had additional people with additional certification? What if we had additional equipment, right? Could we potentially kind of get this production orders out of the door in time? And also, what if we prioritize certain customers or certain orders, right? There are many situations where, in manufacturing settings, managers come in and say, okay, well, we need to expedite this order or this customer because it's a really important customer, but they are not taking into consideration the trade-off, right? They're not taking into consideration the fact that by expediting this one customer, you might be potentially delaying 100 others, right? So if they had that in front of them, would they still be making that decision to expedite that customer? And if you don't do the detailed capacity considerations, the detailed scheduling, and you just do a very kind of a broad capacity consideration where you don't actually schedule everything in detail and schedule every task that actually needs to occur, then you can say, yes, we can still do it, or adding an extra shift is not going to be as impactful, but unless you actually do the detailed scheduling, you're not going to see kind of the real effects of what is going to happen. Another thing that happens is that they overly rely on schedulers and human expertise. And anytime you walk into a manufacturing customer and they tell you basically that they employ 15 people and most of them have been there for 20 years and it takes 2 to 3 years to train someone, then that's a really big red flag for me in terms of like their desperate need of some optimization decision support system to really help them with this, right? Because they're really struggling to actually keep up with the needs of the business. And it's very hard to repair and create schedules in most of these industries. And the other thing is that there are very, very complex dependencies, right? Especially when you're looking at, for example, setup times or cleaning times. When you're moving from product A to product B on a certain workstation, it might take 5 minutes for you to do the changeover to kind of reset that machine. But when you do product B to product A, the reverse, it might take 8 hours to do the changeover time. And the typical example people give there is the painting shop for automotive customers, right? So when you go from white paint to black paint, you just need to change the paint bottles. But when you go from black paint to white paint, all of a sudden you need to do like a complete wash down and obviously clean all the tubes and everything. The other big thing is the WIP, working process inventory synchronization, right? So imagine you're making a simple, for example, T-junction. So you need to create the horizontal bar and the vertical bar, and maybe those are two completely different processes, and you need to kind of create these piles of both of these components before you can go to the end process where you're actually producing the final product, right? So if you don't synchronize these two processes, which again might be completely different processes, then you're kind of failing to deliver on time. You're going to be constantly falling either ahead or behind with one or the other. And finally, everything is dynamic in this world. Just like in the airlines world, you might have new orders coming in, new targets, you might have unplanned maintenance, you might have quality assurance actually telling you that you failed to hit your target and for some quality inspection, and now you need to go back and kind of redo some of these processes. And these things actually apply to many other manufacturing industries, and we've applied them to many other manufacturing industries, right? So automotive, you have this car sequencing problem through different stations. In electronics, basically have the same thing of scheduling of batches, the wafers, through the different stations. In aerospace, it's large-scale assembly. And with consumer products, it's a little bit different again because it's process, but again, the size and timings of batch operations are also fall into that same category. So with that, thank you very much. That's all I had. Any questions? Yes. Right.
Do you have any? So my question was, like, some of these industries you described, they sound like some of them could be low margin businesses, and they don't have the kind of money to invest in the long-term research. I mean, do you see this kind of as a problem, and do you use this as a? What are your thoughts on this?
Right. Yeah, I don't really expect all of these. So each, manufacturing operator to actually start investing in quantum at this stage, right? But in the near term, as others have said, right, when we do start seeing these performance improvements, then there's going to be significant disruption because all of a sudden we'll be able to solve this, right? So maybe some of these technology is going to be available to the low margin operators through independent software vendors. Some of it is going to be available through QAS platforms. And I think mostly vertical and QAS could be the answer for some of them. But there's definitely going to be significant disruption to them.